Hello everyone. Today we're going to be proving the distance formula between a point and a plane in space, in 3D space, and we're going to be proving both the dot product formula and the algebraic version. So this is going to be just an algebraic geometric proof, not going to really use much calculus. So let's get right into it. So first we need to define our plane. That's going to be just our standard equation, ax plus by plus cz plus d is equal to 0. Now, let's just draw that plane real quick. So that's going to be our plane. And we'll have a point in space like this. So our problem is, well, we want to find the distance from that point to the plane. How do we do that? Well, we know from 2D math that if we have a line and a dot, to find the distance between the line and the dot, it's going to be the perpendicular line between them. Let me redo that. Um, Yeah. Now, why is that? Well, because in simple terms, if you draw any other, if you draw the line to any other point on the line, for example, here, it's going to give you a right triangle. And you can see on this right triangle, we have the hypotenuse as this one. So this is obviously going to be longer than this one. So this is the shortest possible length that you can get. So we want to do something similar in 3D space, but in 3D space, we use vectors. So we want to use a normal vector to this plane to kind of find the distance. So let's define a normal vector n. It's going to have the components n1, n2, n3. And we know that this plane contains infinitely many vectors. They can go in any direction as long as they're in this 2D space. Um, and in this 2D space, all of these vectors are perpendicular to this normal vector that's going straight up. So when two vectors are perpendicular, we can say that their dot product, which is their product reflection on the projection onto each other, is going to be 0. So let's define an arbitrary set of vectors in this plane. So we're going to have one fixed point, P0. Let's say this is x0, y0, z0. And we're gonna have another point, let's call it P. So this one's not fixed. It's gonna be like an arbitrary point. So we're gonna say X, Y, Z. So the vector from P0 to P is gonna for sure be in the plane, but it's not gonna be fixed. It just represents the set of all the vectors that's in the plane. So let's call this vector P maybe. So we're gonna say P minus P0 is equal to the vector P, and this is gonna be equal to x minus x0, y minus y0, z minus z0. Now, we know that this set of vectors is the entire plane, and we know that all of them are going to be perpendicular to n. And as I said before, the dot product is going to be 0 when they're perpendicular, so let's write that equation. So the dot product between n and p is going to be equal to 0, and mathematically, it's going to be equal to n1 x minus x0 plus n2 y minus y0 plus n3 z minus z0. Now, if we just rearrange the terms a little bit, so let's write that. I'm just expanding and rearranging. So we get this. Now, what we see is there's kind of a similarity between this equation up here for our plane equation and this equation we just got. So what's the similarity? Well, we see we have an x, y, z multiplied by constants, and we have a set of a group of three constant numbers. So what does this mean? Well, we basically have, as I discussed before, the entire set of vectors in this plane. So it is pretty much just the plane, and we have the normal vector that's to the plane. So this means that basically the corresponding equations must be directly equal for the exact components that they're corresponding to. In other words, that means if I have ax in the first equation, then whatever is multiplied by x in the second equation must be equal to a. That means n1 is just a, n2 is just b, and 3 is just sorry, not z, c. And this set of constants here must be equal to d. Well, it's got a negative sign, so let's just take that out real quick. So I'm going to take the negative sign out and then make these all positive. And now we can say that, well, this set excluding the negative sign is going to be negative d, so that when you have the negative signs cancel out, and what you're going to get is the same ax plus by plus cz plus d is equal to 0. So we've just come back to our exact same plane equation, proving that this is the normal vector. Our normal vector is just going to be a, b, and c. So now that we've kind of established that correlation, found our normal vector, let's go over to the left here, and we're going to look at this plane from the side to start trying to find the distance. So if we look at it from the side, it's going to kind of look flat like that, right? We're going to have the point in space up there. Let's draw a normal vector that we just found. It's going to be kind of going up there through that point. I'll call this normal vector n. And we're looking for this distance, let's say capital D, to avoid confusion with the previous lowercase d. And we're gonna now, we can use the same P0, X0, Y0, Z0 because we just need a random point in this plane to point to that point in space. So let's call this point the same P0, X0, Y0, Z0. It doesn't matter where it is, just that it's in the plane. And let's call our point here maybe Q. We're gonna give it X1, Y1, Z1. So we're trying to find basically the distance from Q to this plane. How do we do that? Well, let's draw a vector between these two first. So going from point P0 to point Q, we have the vector P0Q. And well, we used the dot product earlier, right? We said the dot product is the projection of one vector onto another. Here, we don't necessarily have any perpendicular vectors, but what we do have is still two vectors that, when projected onto each other, give us d. What are those two vectors? Well, P0Q vector has a vertical component that looks something like this. If you just translate that over to the left a little bit, that looks exactly like D. And what is the vertical component? Well, you would need to project onto a vertical vector to get the vertical component. And that vertical vector is what we just found, the vertical vector n. So what we can do now is we can say, well, the dot product between P0Q vector and n vector, because we're trying to find this projection relationship. So now we can use the formula for dot product. We're going to say it's magnitude of P0Q times the magnitude of n times cosine of theta. And what is theta in this case? Well, theta is the angle between the two vectors that you're using. So we're projecting this vector onto the vertical vector. So our angle would be right here. And we're trying to find d, right? Because in our current equation, there's no d. So how do we express d? Well, we know that cosine of theta, which we do have in our equation, we always start from what you do have, is equal to the closest leg over hypotenuse. Well, closest leg is d, so we found our d, and our hypotenuse is P0Q, the magnitude. So how do we get d? Well, all you have to do is move this to the other side, multiply cosine theta by P0Q magnitude. And what do we have? Well, that's exactly what we have in these two terms. So all we need to do is get rid of this n magnitude and move it to the other side. So we end up with, and we can just, so these two together we establish as d. So I'm going to write d on the left side. So d is equal to P0Q dot product n over P0Q, sorry, not P0Q. It's going to be magnitude of n, and that is going to be our equation. Now the top is just a scalar because the dot product just gives a projection scalar. The bottom is a magnitude, also a scalar, and our distance that we're solving for is going to be a scalar. What we do need to do is we need to apply our absolute value to the top just to get rid of any possible negative signs, because it's possible when you do the dot product operation, you end up with some negative parts because of negative components. So we're just going to be safe, add an absolute value there. And that is going to be our first equation. And we now have our positive distance between the point and the plane. Well, what if you're given this plane equation, ax plus by plus cz plus d, and you're given the point and you don't really want to convert all of this stuff to vector format and everything? Well, we can solve for a more algebraic interpretation of this equation. So what we had earlier is we solve for this n vector, and we know our p0q vector is just the basically the traversing distance between this x0, this p0 point and q. So let's write those two out. So I'm going to keep going from this equation, working with, from what we have. We're going to say this p0q vector. So going from p0 to q, it's going to be x is the final point minus x0, y minus y, sorry, y1 minus y0, z1 minus z0, and then times our normal vector of a, b, c, absolute value, all over our magnitude of n. And our n is just abc, right? So abc, the magnitude of that would just be the square root of all of them squared. So now that we have that, let's calculate this dot product. So we're going to work this out. I'm going to put it down here. We're going to say ax1 minus ax0 plus by1 minus by0 plus cz1 minus cz0, absolute value, all over the square root. And now let's look, well, this is a pretty long equation. This shouldn't really be what you're looking for. This is kind of unsimplified. So let's see how we can simplify this. Well, we found earlier while we were trying to find our normal vector that after we took out this xyz part from this normal, I'm going to look at this equation right here. After we took out the xyz, we were left with this expression of n1 x0, n2 y0, n3 z0. Well, what are those? X0, Y0, Z0, that's the same that we have here. We have, and we found that N1, N2, and N3 are basically just A, B, C. So basically we said that AX0 plus BY0 plus CZ0 is equal to negative D. Well, we have the exact same thing here. So we have negative AX0 minus BY0 minus CZ0. And exactly what we did there, this is just, if we just take the negative sign out, that's negative D, then you apply it back again, that's just positive D. So really what all this term is, and this term is just going to be D. So we can simplify that to AX1 plus BY1 plus CZ1 plus D, absolute value, over the square root, A squared plus B squared plus C squared is just going to be your distance. Now, you see that we've solved for this two types of equations. I'm going to say this is D equals to this. I'm going to box it. So we found these two different equations for the same distance that we're trying to solve for. Just based on whatever you're given, you can use either one you want. They'll produce the exact same thing. And you can see that all we used for the first one was this arbitrary vector we found between the point that you're given and a random point on the plane, and the perpendicular vector that we solved for. Uh, I mean, remember, the easy way to find the normal vector is just the three coefficients A, B, and C of your plane equation. And for the second equation, we're just pretty much using that plane equation, except you're plugging in the coordinates of that point in space, x1, y1, z1 in this case. And then you're just dividing by the magnitude of that perpendicular vector, that normal vector that we solved earlier. So we now have two equations, number one, number two. Okay, so now we're going to solve an example relating to these two equations to find the distance between a point and a plane. So from example 5 in the book, we have a point Q with coordinates 1, 5, and -4. And the plane we're given is 3x minus y plus 2z equal to 6. So we want to find the distance between this point and this plane. So how do we do that? Well, our equation is d. So we're going to use both equations. So we're going to start from dot product. We're going to say d is equal to the absolute value of the dot product between PQ and normal vector n with the magnitude of n. Divided by the magnitude of n. So, well, let's find our n first because it's simpler. If we remember, n is just ABC, which gives us 3, -1, and 2. And then to find our PQ vector, we needed to find a random point on the plane that's point P. So we can say point P is equal to, and what we can do here is you can set any two coordinates to 0. So we're gonna set our y and z to 0 here. And what that helps us with is we can greatly simplify this plane equation. We can just plug in the two zeros, and it is guaranteed that there is an x coordinate that gives us a point on the plane. So if we just plug in a 0 in the y, 0 in the z, we're going to get 3x is equal to 6. And we're going to get we're going to solve for x, and x is equal to 2. So we have our point P is 2, 0, 0. And now we can find the PQ vector. So PQ is just going to be from P point to Q point. So that's going to give us from 2 to 1, it's -1. From 0 to 5, it's 5. And from 0 to -4, it's -4. So what does that give us? Well, let's just plug it in. So we're going to start calculating. We're going to say absolute value of -1 times 3. So we're going to say -3 plus 5 times -1, so -5, plus -4 times 2 is -8 over the magnitude. So it's going to be, actually, we're going to just calculate. So it's going to be square root of a squared plus b squared plus c squared. That's going to be square root of 9 plus 1 plus 4. This is going to give us 16 over root 14. And if we want to rationalize this, we're just going to move the square root to the top and then have a 14 on the bottom. And then we could just cancel out the 2's. So it's going to be 8 root 14 over 7. So that's our first answer. Now let's use the other equation to solve it. So our other equation is d is equal to the absolute value of ax0 plus by0 plus cz0 plus d is over the magnitude is equal to the distance. So the x0, y0, and z0 are just the points of the coordinates of the point we're trying to find the distance between. And the a, b, c, d is just our original plane equation. So really all we need to do is plug it in now. So we're going to just plug in all the values. So 3 times 1 is going to be 3 plus -1 times 5, so -5, plus 2 times -4, so -8. And then when we have this original plane equation, the plane equation is ax plus by plus c plus d is equal to 0. So what we actually need to do is move the 6 to the other side, and our equation will become 3x minus y plus 2z minus 6 is equal to 0. So our d is going to be actually -6, not 6. So we're going to have -6 just -6 by its own, because it's not multiplied by anything. D is not multiplied by anything. We're going to have over the magnitude. We found that just before. It's going to be square root of 14. And this top part is going to give us 3 minus 5, -2, minus 8 is -10, minus 6 is -16, and then absolute value is 16. So 16 over root 14, exact same answer as above. If you want to rationalize, it's going to give you 8 root 14 over 7. So we found that no matter which way you want to solve it, no matter which information you're given, we've just solved for both of the same answers using both the equation we solved for previously. Thank you.